Hi and welcome to this video. My name is Pedro Martinez, a professor of hydrogeology at the Universidad Complutense de Madrid in Spain. This video provides a short introduction on MLMapper, a data-driven tool that provides spatial predictions on variables related to water resources. The kind of results MLMapper gets are akin to those provided by traditional geostatistical methods such as kriging. But as we will see, MLMapper makes use of AI technologies. This makes the process more flexible and the results more reliable. By the end of this video, you will know what MLMapper is and the problems it can solve, what you need to run MLMapper, and how MLMapper can be used in practice. So you may be interested in MLMapper if you are a decision maker, a modeler, or a scientist. A crucial issue in providing predictions for water-related variables is how to extrapolate from point source data to the basin scale. For instance, you may wish to predict whether an unmonitored area in an aquifer is likely to be contaminated, or which agricultural areas within a basin are likely to experience problems if there is a drought. Accurate spatial extrapolation is also an important input for many mathematical models. This is where MLMapper comes in. For illustration purposes, let's say we have the Duero Basin in central Spain. The little dots are monitoring boreholes where we have monitored a given groundwater contaminant, like for instance nitrate. The question we ask ourselves is, are we likely to find nitrate in any of those unmonitored areas? MLMapper harnesses the power of AI to make an informed prediction based on what we know about the basin and about the existing boreholes, which gives us a predictive map like this. Running MLMapper requires three inputs. First, we need a target variable, that is, what we would like to predict. A target variable can be anything spatially distributed. For the purpose of this video, we will think of groundwater contamination, but we could also predict the presence or the absence of groundwater, rainfall, or whether an ecological indicator is likely to be fulfilled across a given basin. Second, we need a series of explanatory variables. These are typically easier to obtain than our target variable and contribute to explain it. For instance, a land use map can help us predict groundwater contamination. MLMapper is highly flexible in the sense that it allows you to use a large number of explanatory variables. In our example, we could combine the land use map with a geological map or with a landfall map if we think these are likely to be successful predictors for groundwater contamination. Finally, we need a ground truth database. In the groundwater contamination example, this would typically be your groundwater monitoring network. MLMapper uses part of this database to work out how each explanatory variable contributes to explain the target variable. That is, what combination of, say, landforms, land use, and elevation renders the presence or the absence of groundwater contamination. Then we will use the remainder of the database to test whether MLMapper can predict things correctly. So how does MLMapper actually work? An MLMapper model is typically built within a GIS environment. First, you compile your dataset of predictor variables. We can use as many as we want. MLMapper will look for the correlation of pixel values for each predictor variable that results in a given borehole being contaminated. As soon as MLMapper reaches a suitable accuracy threshold, for instance, once it provides accurate predictions in over 90% of the cases, we can use it to extrapolate for the whole of the study area, since we know every pixel value for each one of the predictor layers. This effectively gives us a predictive map. The MLMapper workflow incorporates many state-of-the-art tools to enhance the predictive ability of the models, as well as their interpretability. In Stars for Water, MLMapper has been used to predict groundwater contamination in the Duero Basin, Spain, and in the East Anglia region, United Kingdom. We have also used this software successfully to underpin siting of water supply boreholes in low-income countries, to delineate groundwater-dependent ecosystems, and to predict the properties of soils, to list a few examples. In summary, MLMapper is a highly versatile, data-driven tool that can help us obtain accurate predictions that are relevant for water resources management. If this sounds interesting to you, I encourage you to check out a more in-depth tutorial of how MLMapper actually works in the Stars for Water Academy. Thanks very much for watching, and see you next time.